Okay, folks, for this screencast, I'm going to show you a cool way to simulate control block diagrams using a program called Scilab. If you don't know what Scilab is, it's free. You should download it. It's very similar to MATLAB. I can make a linspace variable here. I can plot x. I can make, and it makes a plot. Very, very similar to MATLAB. I encourage you to download it. It also has a program called Xcos, and Xcos here is very similar to something called Simulink. If you've ever used Simulink, you have control blocks like this that you can drop onto a pane here, and so I'm just going to jump right into it. I'm going to drop a transfer function into my workspace here. I'm going to double click this guy. I'm going to make this a second order system. This is an example problem that I've done in class. This is the angle of attack dynamics for a aircraft. First I'm going to do open loop, so I'm going to make a source step function, and so I'm going to drop the step function in here. I'm going to have it start at 0, 0 and end at 1. I'm going to connect this up, move this over, and then I'm going to make another sync, and I'm going to make a scope. And so I'm going to connect this up. I'm going to hit the up arrow on my keyboard to move that up. And then I'm going to double click the scope here. I'm going to make the y min 0 and the y max 1.5. I'm going to make the refresh period 10 and the buffer size 10. I also need a source clock that's going to sort of tell the simulation like what to do. So it has like some period and whatnot. Then I'm going to go to the simulation environment, the setup routine. And this is really important. You have to change the final integration time to 10. You don't have to, but I'm just doing it to 10. But the really important thing is that you want to change the solver kind to Runge-Kutta. And I'm pretty sure this is a Runge-Kutta 4.5, so it's using an adaptive time step, which is why you can't set this. And you hit OK, and you run it, and automatically this plot pops up. And this is exactly what I expect. This is a critically damped system with a settling time of 4 seconds. I think it might be 2 seconds. I forget. I forget what the poles are for this thing. But anyway, and there's steady state error because 3 divided by 4 is 0.75, so that's the final value it goes to. All right, so if we want to add control to it, what we can do is we can move the step out, and then we can go back to continuous systems and just grab a PID block. And we're going to connect the output of the PID block to here. And then we need a summer. I think that's a mathematical operation. We're going to grab the summing block. The error signal is going to hit the PID routine. The step function is going to be our command. And then we need a unity feedback signal, but because this is a summer, we actually need a gain block. And I'm going to flip this, or mirror this, sorry. And I'm going to double click this, and I'm going to change this to -1. So that way it's negative feedback. I'm going to click and hold my mouse, drag it over, let go of my mouse, and then push my mouse up. And that way I get a nice right angle. And then I'm going to do the same this way, and then move it up, and then there we go. And so now I've got nice unity feedback. I'm going to double click this PID block. I'm going to make the proportional gain for the integral gain 0. I've already done a Routh-Hurwitz table on this, and I've already designed this PID controller, and so I did this in class, and so I already know what these gains are. So if I simulate this, it's not really going to change much from before. The only difference really is that the steady state error is a little bit smaller than before because of that proportional gain, and we moved the settling time to exactly 2 seconds. Now if we go into the PID block and add some integral gain, like 3, now we should expect the steady state error to go away completely, and there you go. So now we have no steady state error whatsoever. And that's it. That's basically in a nutshell. That was very fast. If you have questions, post them in the comments, and hopefully you can simulate as much as you can using Xcos, which is 100% free, and I encourage you to download it and use it.